Okay, so in this video we're going to review how you can use the Bernoulli equation together with potential flow to compute pressure distributions in a fluid flow situation. Okay, so potential flow is a branch of fluid analysis where the goal is basically to obtain basically spatial distribution functions for the velocities. And so, you should be able to get these field functions here where if you plot them, you get these very nice figures, very nice distributions of velocity that show you basically exactly what the fluid's doing. And so you can show you the direction, which direction the flow is going, as well as its speed as well. And that provides a wealth of information that you can use for lots of other analysis in fluid mechanics. And the way that we do that is we use this specialized function called the stream function, which is a scalar function that follows Laplace's equation that can be differentiated to obtain the velocity components, right? And so, being able to find the stream functions and take its derivatives is basically how we perform potential flow analysis, right? And it just so happens that all the assumptions that we made for potential flow, mainly incompressibility, steadiness, and inviscidness, mainly that the viscosity is minimal inside potential flow, these are all the same requirements that are needed for the Bernoulli equation as well. And so what we can do is we can combine the two. And so we can first use potential flow to find the velocity components. Okay, then we use that to compute the speed. Then we can then plug that into Bernoulli to compute spatial distributions of the pressure as well, which is also very valuable information and quite uncommon actually. There's not that many places in a introductory fluids class where we can compute the pressure field as directly as this. Okay, so the example I'm going to show you on how this all works is flow around a cylinder, and so here is our stream function for that. I've went ahead and put this in a slightly more convenient form, and so these two functions are the same. I've just kind of rearranged them a bit. Where this a right here, this a here is the radius of the cylinder, right? And so this will be a bit more convenient for us to do because once we take the derivatives here to compute the velocity components, what we can then do is we can plug in the radius of the cylinder A in for R and then compute the velocity at the surface of the cylinder. Okay, and so this simplifies things quite a bit for us. And so at the surface of the cylinder, we see that we have no radial velocity, and our polar velocity is this 2 sine theta. Okay, and so now that we have both velocity components known, we can then compute the speed by taking the magnitude of these two components. Okay, and what we get is that the speed here is 2u sine theta. And so now that we have the speed, we can then plug this into the Bernoulli equation to compute pressure. Okay, and so here we have the Bernoulli equation. And remember, the way that we apply Bernoulli is that we have to consider kind of two different points in the flow. Okay, and so on the left-hand side of the Bernoulli equation here, we're going to consider some point that's far away. Okay, and so the point is so far away that we know the pressure there. The pressure there is going to be P0, but it's going to be so far away that the fluid's going to be at rest. And so the velocity term here is going to be 0. One other assumption that we're going to make is that this faraway point is selected such that the height difference is negligible. Okay, and so we're going to cancel out those terms. And then on the right-hand side here, we're going to plug in the conditions at the cylinder surface. Okay, and so for this velocity here, we're going to plug in our u expression here. And then from there, we should be able to solve for P2, where P2 here is the pressure on the cylinder. Okay, so if we work through the math for that, of course, I'm skipping some algebraic steps. But what we get is the pressure on the cylinder is P naught, the faraway pressure, minus 1/2 rho u squared times 1 minus 4 sine squared theta. Okay, and this is really interesting because if you think about your polar coordinates for a second, this theta kind of tells us where we are on the cylinder, right? And so if we compare a point at the front end of the cylinder, okay, and so the front end of the cylinder is given by theta is equal to pi. Okay, so if you rotate around here, you see that our polar angle is pi right here, and we compare that to the downstream side of the cylinder. So the part of the cylinder that's on the back side here, which is theta is equal to 0. What you'll see is that the pressure, right? If you plug theta is equal to pi and theta is equal to 0 into this expression, the pressure is going to be exactly the same on the front and the back. What that means is that if you're standing in a uniform flow, I know it's a cylinder, but if you kind of stand up, straight, and then kind of look at yourself from above, you're basically a cylinder. You're not quite a Jigglypuff from above, but you're cylindrical in shape. But so that means if you're standing in a flowing fluid that's flowing past you, you're going to experience no drag force, which, if you've ever stood outside on a windy day, is absolutely not true. And so this kind of paradox is known as D'Alembert's paradox, meaning that, if you just analyze the situation with potential flow, you end up with a paradoxical result, which is not true. Okay? And what kind of fixes this paradox is the fact that, remember, the fact that we're using Bernoulli and the fact that we're using potential flow means that we've ignored viscosity in this whole process. And so what this tells us, or what D'Alembert's paradox tells us, is that in order to compute a lot of drag forces, you need viscosity. Viscosity is required in order to get any kind of drag forces in a situation like this. Right? So that's kind of an interesting result, but this example kind of illustrates also how you can take a potential flow solution, combine it with Bernoulli, and get a function for the pressure on a surface like that.